no trip during normal and balanced current and provides adequate trip in the specific and correct zone during an actual ground fault condition. Okay, we'll stop for a moment. Okay. As we said earlier, the differential ground fault protection system, as we designed, not only works for a main system or main time main system, but they can be employed with a number of power systems. We have designed systems over the years where we've had multiple systems, some as many as 12 sources of power and 12 breakers. 12 breakers, 12 ties, not uncommon. Now, as we said earlier in the presentation, people are wanting more sources of power, more reliable source of power. The perception is more is better, and now is best. It's not uncommon to have a system where we used to have a main time main system. Now we literally produce over 2,400 systems a year, and over 50% of those have more than two sources. A common configuration is one where there would be a generator and a main breaker feeding one load bus, a tie breaker in the middle, and then a generator and a utility feeding another load bus. We would call that a generator main, tie, main generator. Now, these systems for us are very common. However, they require a specific type of expertise in order to design them and to install them in the field. That's why we provide detailed records to installing contractors how to make the interconnects. You can imagine that if you have multiple sources of power and multiple ties, all of these different power systems cannot be manufactured in one lineup of switchboards or switchgear that's shipped as an entire unit. They are a one lineup. They make up many sections of systems. For example, if we have a system that has 12 main breakers, be a combination of generators and utilities, and we have 12 ties and a ring bus, that is at a minimum 24 sections of switchboard or switchgear. And that's excluding the distribution sections in between. That is one long lineup of power distribution equipment. All of those sections must be shipped individually, such that when they're received on site and lined up and installed and terminated by the installing electrical contractor or facilitator, all the interconnects for all the ground faults have to be properly made, which is exactly why the National Electrical Code required that under Article 23095C that such systems be tested when first installed on site to ensure that they operate. And this is extremely important as you get into multiple sources of power system, be they from generators or utility. This is going to become more important as we starting to change the power distribution system in our country, where we are going to employ alternative energy sources, be they from windmills or solar panels. These systems will operate in closed transition or operate closed, linked together with the normal power source all of the time. And they will require a differential ground fault protection system that must be adequately designed, properly installed, and assured to be operating via a test procedure in the field. Not only is the code requires they be tested when first installed on site, Square D recommends they be tested annually as part of our operation and maintenance process. However, we're aware that this rarely occurs because in order to test them, they have to be turned off, and you have to bring in test equipment to do high current and primary injection to simulate normal and balanced current and actually fault currents during a high current, low voltage, non-destructive testing. Most facilities, after their first commission, do not perform these tests afterwards, even though they're recommended. But I want to make the point that as you add more power systems to a power distribution system or create a very, very complex power distribution system, it's extremely important that registered professional engineers be commissioned that are experienced with these type of systems to help design them and install them and test them. Now, the engineer doesn't have to be there for the installation, but in many cases it requires an expertise to supervise or during the commissioning stage. Schneider Electric provides that service, but there are other competent facilities and competent engineering companies that can do that. But the point of it is find someone that's experienced in those type of systems, that knows what they're looking at, how they should be tested, as well as what to do when they're not tested properly or not operating properly, how to fix them and how to troubleshoot them and how to repair them. And to provide the study. As you have more and more power sources, specifically where they're tied together, your available fault current goes up dramatically. Consequently, your need for a selective coordination study to operate your system effectively with coordinated settings and to limit the available arc flash is very, very important. This requires a specific type of engineering expertise. Now, how do these systems work? As you have more and more power systems, you require more and more sensors and more relays. For example, each breaker comes with the type of sensors we predominantly use are residual sequence sensing, such that each breaker has a minimum of one sensor per phase and one sensor per neutral. As we said earlier in the presentation, Schneider Electric can provide power systems up to 6,000 amps, where you have a circuit breaker that provides 6,000 amps of power. Such systems are very, very large, such that we provide 2 sensors per phase. We're actually splitting the bus in the back of the breaker. So each breaker would have a total of 8 sensors per breaker. And in a standard main time main system, that's 24 sensors and 3 relays. Now, as you go up in size, you add more breakers, you're adding 24 more sensors and another relay. And it doesn't take very, very long for you to realize the complexity. For example, in a standard main time main system where you have a 4,000 amp breaker, there are 24 current sensors and 3 protective relays that must be specifically designed and differentially connected together. Of those 24 sensors, just in a main time main configuration, there are 24 to the 23rd power combinations of how to wire them. However, only one will work. The trick is to know which one of those millions and millions of possible combinations work. And you can interpolate that to see such that if you go out to a higher complexity system, such that you have a generator main, tie, generator main, and a 4,000 amp breaker, you now have 5 breakers times 8 sensors. That's 40 sensors and 5 relays that must be differentially connected together. The total number of possible combinations for that system is 40 to the 39th power. That's how many possible ways you could wire it together. You must have a specific engineering methodology in order to employ that. You cannot use trial and error. It would take your entire lifetime to figure it out. That's why you need specific engineering expertise in order to do these systems. Now, the argument is in the industry is that we can avoid all this complex ground fault issue by using 4-pole breakers. Yes, if we take a standard main time main system and we use 4-pole breakers, then we would not have to employ a differential ground fault system, in that the neutrals would never be tied together and that the power system would never have 2 main bonding jumpers and 2 system ground bond jumpers connected together. That would work fine, such that if you had a main time main system and all the breakers were 4-pole, if I had an interruption with one service, I would open up that main breaker, close the tie breaker, and then I would have a radial system. However, I would have to adjust my design to incorporate the installation of the tie breaker in order to get proper selectivity. And in addition, if I ever use that system in a closed transition operation such that my tie breaker and main breaker are tied together, then I would need a ground fault system, because if I use 4-pole breakers,